In this video, we're going to take a look at the sandwich or the squeeze theorem to see how we can find the limit of a special sine x expression. Now, to start, make sure that for when we're looking at trigonometric functions in calculus, we're going to use radian measures. And for continuity, remember that sine x and cos x are continuous everywhere. Now, tan x, cosecant x, secant x, and cotangent x, we say they are continuous everywhere, except at the points where they are undefined. So that's where an asymptote will be occurring. So the theorem says that if c is any number in the natural domain of the stated trigonometric function, natural domain means that this is the normal domain where the trig functions will exist, then we have the limit of sine x, cos x, tan x, cosecant x, secant x, and cotangent x. We can find the limit just by plugging in c for the value of x in each of the trig functions. So we have sine c, cos c, tan c, cosecant c, secant c, and cotangent c. So basically we just have to plug in the c value for whatever x is to find the limit. Now I'm going to show you a special limit that that you often use when we're looking at trigonometric functions. So we're going to use something called the sandwich or squeeze theorem, and it states that if f of x is less than or equal to g of x, which is less than or equal to h of x, for all the x values in some open interval containing c, then if the limit of f of x as x approaches c, which is, notice it's the first function, and the limit of h of x as x approaches c, which is the last function, and they both equal L, then we should know that the limit of g of x when x approaches c should also equal L, since it's squeezed in between the two functions f of x and h of x. So taking a look at this graphically, so let's say that we have some function f, and we have some function h, okay, then g of x is in between so that at this point here, since x is approaching c, and the limit of c for this point for f of x and h of x is going to be L when I draw this line across, then for g of x at that point c, the limit should also be L. So we're going to use this sandwich theorem to prove this theorem here, which is that the limit of sine x divided by x as x approaches 0 is equal to 1. Now, let's show you this graph here. So this graph shows y equals sine x and y equals x, which is my numerator and denominator in this function that I want to show you. We can see that as we get really, really close to 0, it actually looks like it's the same line. So as x approaches 0, x is approximately the same as sine x. So this approximation is used in many different applications. So in terms of limits, this approximation says that as x approaches 0, sine x divided by x is equal to 1. So if I actually plug in 0 for the numerator and 0 for the denominator, we're going to get 0 over 0. So that doesn't really work for us. So what we're going to do is we're going to use the squeeze theorem to derive this limit here. Now, it's not a formal proof, but you can think of it as an argument, which makes it plausible. So we're going to use a little bit of geometry as well to figure this out. So let's say that we have this circle, and we have theta as the angle here, and r is the radius. So we have this sector area here, which I'm going to shade in. So the area of the sector is proportional to the area of the circle So then we can say that the sector angle has to be proportional to the circle angle. Now by circle angle, I actually mean the entire circle. So the area of the sector, we would say, is the area of the sector. Area of the circle is pi times r squared. Sector angle in this case is theta. And the angle of the entire circle we know is 2 times pi. So if I multiply both sides by pi r squared, I have that the area of the sector is the pi's cancel off, and I'm going to have half r squared, and I also still have a theta. So what we're going to do is we're going to use this formula to find the sector area below. All right, so we're going to use the unit circle to find the areas, and you'll see how this eventually leads into the limit. So with respect to angle x, so I'm going to draw an angle here, and I want it to extend all the way out so that I could also draw this. Okay, so we're going to say that this is angle x. I know that this is going to be 1 since I'm using a unit circle. Okay, and this point here is going to be 1, 0. And I'm going to draw another triangle inside here. So both of these will be right triangles. So this line here is also going to be a length of 1 because it's the radius of the circle. Now we have another point here, and you've learned from your work with trigonometry that this has to be the point cos x and sin x. Okay, so you can watch one of my trig videos to find out why this is so. Okay, so here we actually have another point. So this is 1. So we know that this value here is going to be 1, and then tan x. So tan x, because we have the opposite, which would have been, let's say this was y. So tan x, if you want to show yourself why this is true, tan x would equal, let's say this vertical is y value, y divided by 1, which is this horizontal distance. So the y must equal tan x. So the y value here in the point must be tan x. All right, so now we're going to find these areas. So the little triangle L, in which I am going to say is this triangle here. Let's draw this in red. Okay, so the little triangle L it has a height of sin x. Okay, so we can say that the area of the little triangle is base, which is 1, times height, which is sin x, divided by 2. So this is base times height divided by 2 to find the area of a triangle. All right, our next triangle that we're going to find is the sector S. So I'm going to redraw this again. This will be this triangle here, and then including this rounded part here. All right, so that would be this rounded part there. That looks something like this, and this would be x. Oh, and I should probably show that this is x too. All right, so the area of the sector is equal to, according to my formula from above, half times r squared, which is 1 squared, times theta, which is x. So here I have x divided by 2. All right, finally we have the big triangle, which is this one here. Okay, so the big triangle, this is x, this is a height of tan x, okay? Right triangle here. So the area of the big triangle is base, which is 1 times tan x divided by 2. All right, so according to this, my little triangle should be the smallest. It's smaller than A of S, which is a sector, which is smaller than the big triangle, the area of the big triangle. So I'm going to substitute these expressions into this inequality. So sine x over 2 less than or equal to x over 2 less than or equal to tan x over 2. Since they're all divided by 2, I can get rid of them by multiplying them all by 2 if you like. Okay. However, we also know that tan x is equal to sine x over cos x. From my trig identities. Okay. Now I see that a lot of the expressions have a sine x, so what I'm going to do is I'm going to divide every expression by sine x. So when I do that, I'll put brackets around here, I get 1 is less than or equal to x divided by sine x, which is less than or equal to 1 over cos x. Now as x approaches 0, because remember that our limit was x approaching 0, we know from the cosine graph, which I'll draw over here, as x approaches 0, my cos 0 becomes 1. So this expression becomes 1. So therefore, this expression here then becomes 1 is less than or equal to x divided by sine x, which is less than or equal to 1. So here we can see that by the sandwich theorem, since my lower and upper inequalities are 1, then the limit as x approaches 0 of x divided by sine x must also equal 1. Now if I take the reciprocal of everything, this would still be 1, this would still be 1, and I would take the reciprocal here, then I would also have sine x over x. So taking reciprocals, I have that the limit of sine x divided by x as x approaches 0 is equal to 1. So that's just saying that I have 1 less than or equal to sine x divided by x, which is less than or equal to 1. So this gives me this theorem here, which states that the limit of sine x over x as x approaches 0 is equal to 1. Okay, and then we can also find a proof for this one here, which you should also memorize, that the limit of 1 minus cos x divided by x as x approaches 0 is 0. Now it's not actually that similar to this first one here, so this is something that you should memorize. All right, so I've shown you the limit of sine x over x as x approaches 0 is equal to 1. And then I'll show you in another video how to apply this theorem.